Optimism for non-techies. In this lecture, you learn about optimism and why we think that is the way forward for Ethereum. This is not supposed to be a very technical lecture. I'm going to assume you understand, roughly speaking, what Ethereum is, but that you don't have very detailed knowledge. When necessary, I'm going to explain background information. Agenda. What are we going to do? We'll start with why Rollups. Why do we even need to improve Ethereum? Why isn't Ethereum performance good enough? Then we'll talk about why rollups are the solution, or at least why I, as an employee of Optimism, think that they're the solution and how they work. After that, we'll talk about bridges that allow you to transfer messages and assets between L1 Ethereum and the rollups. And finally, we'll talk about additional resources and where you can learn more about this. Why don't we just use Ethereum? Ethereum is great, but it may not scale enough. Why? Because it has limited capacity. From time to time, this leads to congestion. Congestion leads to high gas costs. And the reason is that every transaction needs to be executed. Currently, I'm doing this lecture pre-merge by thousands of computers, every node on the network. After the merge, it might drop to a few hundreds, but that is still a lot. So transactions are expensive. Are they too expensive if we have William Whale who has 1,000 ETH and wants to convert some of them to a USDC, a stable coin? No, he can afford it. But what about poor Jose from Peru? He needs to transfer $3 to the doctor for his ailing grandmother. He can't afford the gas fees. That's why we need to build a more scalable system so that Jose can also use Ethereum. How are we going to do this? By reducing the load. Instead of doing everything with Ethereum, we will use Ethereum just as our dispute resolution mechanism. Let's take an example from daily life. Checks. We have a dispute mechanism in our society that is called courts. It is slow, it is very, very expensive, but it exists. However, you don't go to court to cash a check. You only go to court if the check goes bouncy, 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 bouncy. However, because courts exist, passing bad checks is bad policy. It's going to cost you a lot more than it is worth, and that ensures that checks usually don't bounce. What we want to do is something similar with Ethereum. Change Ethereum to our dispute resolution mechanism, the mechanism that we will use only if there is some kind of problem, and of course this means we need to provide it with all the information necessary to know if there's a problem. Now it's time for some background information. Let's talk about the blockchain trilemma. What is this? There are three things that we want in a blockchain. Of course, we want it to be secure. The whole enterprise is pointless if we can't trust the information. We also want it to be decentralized, though, which means that you won't have one or a few central authorities, central nodes that can falsify information. And we want it to be scalable. We want to be able to do as many transactions per second as necessary. You can get 2 out of 3 easily. 3 out of 3 is a problem. For example, classical IT, let's say what your bank uses, has scalability with security. They can do a lot of transactions, but that is because they only have a few servers that they control that hold the database, and if they wanted to zero out your account, technically they could do it. Blockchains typically work on decentralization with security. This is the priority in Ethereum. However, this means that we need to have a sufficiently small block size and a sufficiently large amount of time between blocks that everybody should be able to buy a laptop and use that to run a node. And to achieve this level of decentralization hurts our scalability. Improving scalability and decentralization is at the same time is difficult because decentralization means you have lots of different servers, and scalability means that you need to process transactions very fast, and there has to be one canonical order of the transactions. Otherwise, I could give you $5 on this server, give somebody else the same $5 on that server, and yes, we're scalable, we're decentralized, but we are not very secure. Ethereum gives us several features. One feature is data integrity. You can't fake information. This is because every transaction is signed by somebody who is authorized to do it. Also, there's data availability. Every node has the data to verify the blockchain state. What do those two mean? Let's say that you sent me 5 ETH yesterday. I can't come today and say, no, you sent me 10 ETH. I should have 5 more ETH in my balance, and I can't do it because your transaction is signed with the amount 5 ETH. Data availability means that you can't come and say, why is there 5 ETH missing from my balance? I never sent them. Because every node has the data, so everybody can see that yes, you did send them to me yesterday. In addition to this, there's secure computation and secure internal storage. And the reason for that is because thousands of computer nodes and running in thousands of places by thousands of different organizations can't all plot to deceive us in exactly the same way. So if the Ethereum network said that they calculate that something happened in a certain way, probably that's the way it happened. So, since we are using some features from Ethereum, we are essentially building on top of it, so we call Ethereum itself Layer 1, and the systems that are built on top of it, such as Optimism, Arbitrum, Starkware, etc., we call Layer 2. And we offload whatever we can, whatever doesn't absolutely have to happen on Ethereum, which usually means the secure computation and the secure internal storage. Of course, this means that we need to have some other mechanism to ensure that this functionality that we offloaded is still secure. The type of layer 2 solution we'll talk about here is Rollups. Rollups write all of their transactions to Ethereum L1, meaning that we inherit data integrity and data availability. Instead of calculating the results of transactions on thousands or hundreds of nodes, we calculate them someplace else for cheap, and we have a mechanism to ensure that the reported results, the reported state after the transaction is accurate. For the mechanism that we use to ensure transaction results are accurate, to make sense, we first need a little bit more background information. First, let's talk about node software. Node software is the software that actually runs the network. It can be Ethereum, it can be Optimism, it can be Arbitrum, etc. on a computer, and there are several options. There are several clients that are compatible with each other. In the case of Ethereum, there's Geth, Aragon, Besu, Nethermind, and there are a few others that are less popular. These communicate transactions and finished blocks in a peer-to-peer method, so anybody can talk to anybody. Each of those nodes verifies that the blocks are legitimate by running the transactions internally. How does that work? How do we run transactions? The answer is virtual machines. The term virtual machines means a computer that is running on top of another computer as a piece of software. And one common example is the EVM, Ethereum Virtual Machine. We have a physical computer. On top of the physical computer, we have node software. Let's say Geth because that's the majority of them. Part of the Geth itself is the EVM, the Ethereum Virtual Machine, and that virtual machine runs the smart contract. Why is this important? Because the verifying that the EVM ran correctly is exactly the way that we verify that transactions are processed correctly. One type of rollup is the zero knowledge rollup. It got this name because it calculates a zero knowledge proof that a transaction was executed correctly. Never mind what zero knowledge is. It's a mathematical term that's not very relevant. What's important is that while creating the proof is an expensive, complex calculation, verifying the proof is something that is very cheap, very easy to calculate, so it can happen on L1, and that gives us the answer, and that proves to us that the proposer is honest and that the transaction was executed correctly. The problem is that it relies on very complicated mathematics. It may or may not be feasible to run the EVM, the Ethereum Virtual Machine, through zero knowledge proofs like this. The reason I say it is because it is definitely possible in theory. Zero knowledge proofs have been proven to be something called Turing complete, which means that anything a computer can do, they should be able to do. The question is the performance. And the other issue is that because the math is so complicated, it is difficult to find people to audit the code and verify that it works correctly. This is, of course, a major consideration in security systems like blockchains. The other type, and what Optimism does, is called an optimistic rollup. Optimistic rollups post the results on L1 immediately after, or soon anyway, after running the transaction, but then there is a fault challenge window for others to dispute them. Instead of relying on math, they rely on economic incentives. If you post the correct result as the proposer, you get a reward. If you dispute an incorrect result as a verifier, you get a reward. If you post an incorrect result, however, as the proposer, or if you dispute a correct result as a verifier, then you lose the stake that you need to put in. Why it's bad to post an incorrect result is obvious. The reason that disputing a correct result also has a penalty is because it otherwise could be used as a denial of service. I object, I object, I object, I object, I object, and that way slow everything down. So we make it expensive to do it. The way this works is using fault challenges. They were originally called fraud challenges, and you can still find that term in a lot of places. However, we decided to rename them to fault challenges because incorrect states are likely to be accidental rather than malicious. How does that happen? There are two steps. The first is bisection, getting to the one step where before it the proposer and the challenger agree, after it they disagree, and then we execute this one small step on L1. So, how does it work? There are three entities. There's the proposer, which is a piece of off-chain software that proposes what the post-transaction state should be. Then you have the verifier, another piece of off-chain software. This one checks if the proposer proposes the right state, and challenges if it isn't. And finally, you have the arbiter. That one is an on-chain smart contract. The source code is known. Everybody can trust it. It holds stakes from the other participants. It receives their claims about the state, and it runs the single step to actually decide. So let's start looking at it. Before the transaction in question, let's say that the proposer and verifier agrees. The proposer says the state is S0. The verifier says, you're right, it's S0. Then the proposer proposes after the transaction, the state is S7. The verifier responds by sending a transaction to the arbiter. Your proposer is crazy. It is CS7A. The arbiter then says, well, we know you agree on the state before the transaction. We know that you disagree on the state after the transaction. Let's start looking where exactly is the disagreement by doing bisection, by looking at the middle. So after step 4, what is the state? The proposer says it's S4, duh. The verifier says, what drugs are you taking and can I have some? It's S4A. Completely different. The arbiter then says, okay, we know the problem is step 4 or earlier. Now let's see what the two of you say about the state after S2. The proposer says S2. After step 2, it's state 2, S2. The verifier says, you know something? For once you are telling the truth. It is indeed S2. So the arbiter says, okay, now we know that you both agree on the state after step 2. We also know you disagree on the state after S4. This means that either step 3 something happens that causes you to disagree on, or step 4 something happens that causes you to disagree on. Let's see what you think about the state after step 3. The proposer says it's S3. The verifier says you are back to your old tricks. It is S3A. And now the arbiter says, okay, you both agree it's S2, then you run S3 and you disagree on the result. So I will run S3 and what I say goes, because I'm a smart contract and everybody knows that they can trust me, right? Before we actually go into how it runs that one step, though, we need a bit more of background. First, what programmers like to write their programs in a language like Go, for example, which is what you see here in the white frame, and it does something, it's pretty readable. Computers, however, don't read that kind of code. What computers need to execute is a bunch of bytes, a bunch of binary numbers that tell them exactly what to do. The software that converts the first one to the second one is called a compiler. So how do we run the one step on L1, which is done by the arbiter, remember? In the case of Arbitrum, they transpile, which is translate EVM to AVM, Arbitrum Virtual Machine, and Arbitrum Virtual Machine is written in such a way that it would be easy to execute one AVM step. In the case of Optimism, we still are working on it. It's work in progress. We're not there yet. But the way that we're going to do it is to compile the node software, and we are going to use Geth to a format called MIPS. It's not the complete Geth, it's a subset. We call it mini Geth. Then we run this MIPS as a virtual machine on the EVM. So we have a physical computer running Geth. Inside Geth runs the EVM. Inside that we have the MIPS VM, and that is running mini Geth. This sounds like performance would be terrible, right? The only reason it sounds to you like performance would be terrible is because you do not need the hearing aid. It is terrible performance. However, we only need to run one step of the MIPS VM, so it's not going to take that long. And Arbitrum is also working on a similar system called Nitro. Let's put it all together. All the transactions are written to L1, and anybody can verify the state of the blockchain at any point. The state commitment is probably going to be accurate. Why? Because if there is at least one honest verifier, then they would challenge incorrect states, and therefore you would get to the correct state eventually. And the economic incentive aligns with honesty. An honest verifier would make money, whereas a dishonest proposer or a dishonest verifier would lose it. So let's see what it looks like. There are two places on L1 where we store information. One is the canonical transaction chain, and one is the state commitment contract. So in the CTC, we have block A. It is transactions 1, 2, 3, 4. In the state commitment contract, we have our state after transaction 4. We don't do it for each and every transaction. We just do it when we get to it for the currently latest. Then we have two more transactions. We write them to the canonical transaction chain as transactions 5 and 6. Then we write 7, 8, and 9 as block C. And it's been long enough, so we also update the state commitment contract, and we have published the state after transaction 9. This means that if we're going to have a challenge, a fault challenge, the challenge will have to start with agreeing on the state after transaction 4, disagreeing on the state after transaction 9, and then again with bisection it will see where exactly is the disagreement on which transaction, and then find exactly which step is the disagreement. Where is all this implemented? In a piece of software called the sequencer. The sequencer receives transactions from two places. It receives transactions from the web because it exposes an endpoint, a web server that other programs can contact. And it can also receive transactions from L1. It is more expensive to send the transactions on L1 since you need an L1 transaction. However, that is uncensorable. On the other hand, if we as the sequencer receive the transaction through the internet, we can always pretend we never received it and censor and prevent access. So the L1 blockchain is really a safety mechanism here to prevent that censorship. Then the sequencer writes the blocks to L1, to the CTC, the canonical transaction chain, and it proposes new post-transaction states to the state commitment contract, and those can then be disputed by verifiers. This isn't the early days of Bitcoin. People already have various assets on the Ethereum network, and they don't want to deal with a whole new and unrelated set of assets. They want to transact using those assets that they already have, just at a lower cost on an L2 system. So the solution, what's the solution? We create entities called bridges, and we use them to transfer assets between L1 and L2. There are two types of bridges. We'll start with the trustless bridges that use the same mechanisms used by the Optimism rollup itself, and then we'll talk about the trusted bridges that rely on you trusting that whoever runs it is being honest, but that can be a lot faster and cheaper because of it. Okay, trustless deposit. How do deposits work? The user on L1 on Ethereum calls the L1 bridge and sends it assets. In the case of ETH, the user just sends the asset directly. In the case of ERC20, the user gives the bridge an allowance and then calls the bridge and says, hey, you have this allowance. Either case, the bridge does two things. First, it holds the assets, it locks them in the bridge, and then it sends a message to the bridge on L2. Hey, L2 bridge, listen, this user, let's say Bob, just sent me this asset. The bridge on L2 then mints the equivalent asset on L2 and gives that asset to the user from L1, typically. So this is how you get assets on L2. Now, Bob is going to use this asset, is going to transfer it. It's going to go through here, there, everywhere. Eventually, somebody else, let's call her Ada, will get it, and she will want to withdraw it back to L1. How is she going to do it? She again sends the assets to the bridge. Now, the L2 bridge does two things. First, it uses a match, it burns the assets on L2, and then it sends a message to L1. Hey, L1 bridge, listen, this address, let's say Ada, just sent me this asset, I burned it, you need to release the equivalent asset on L1 and give it to Ada. Nothing happens for a week. Why? Because that's the time for fault challenges. So for a week, Ada sits there, waits. The assets are essentially in limbo. And we are waiting to see if there's any challenge or there isn't. Let's say that there wasn't any challenge during that week. Now, Ada can send a claim transaction on L1 that goes to the bridge and says, hey, bridge, can I have my assets? You got a message that sent them to you. And of course, she doesn't say you got a message that sent them to you. What she actually says is, this is a Merkle root of the state. And here is the Merkle proof that part of that state is that message that you need to release those assets to me. And the L1 bridge checks that message, verifies it, and releases the L1 assets back to the user, in this case, Ada. Now, a trusted bridge is faster, but you have to trust the bridge software. The bridge, in theory, could cheat you. So how does this work? The user sends the assets on one layer, and the bridge then sends them back on another layer. The user must trust the bridge, and the bridge has to trust the optimism state, and is therefore likely to run a verifier. So how does it work? Let's say Ada sends an asset again now to the trusted bridge on L2. So the bridge on L2 now has more assets. The bridge serves and it sends that message to send it to Ada on L1 to the bridge server. When we say send a message from the blockchain to something that is not the blockchain, it's essentially an event, emit an event. The bridge then goes to the L1 bridge. So the bridge server then goes to the L1 bridge and says, hey, listen, you need to send Ada this amount of this asset. And it is usually minus a fee. Those things are for-profit businesses. However, that fee is usually a lot smaller than the fee than the cost of verifying a Merkle proof on L1. So this is a much cheaper way to do a withdrawal. The L1 bridge then sends the assets to Ada, and its asset pool gets smaller. So how do these assets pools work? They often come from liquidity providers. As you get a low return for putting the assets there, but it is a solid investment. It is backed by real assets that just take a bit of time. So it's I do it. This is where I have some ETH. And the bridge can always use the trustless bridge to balance out assets. So if it says, for example, that people usually do deposits on our bridge because it's fast, but do withdrawals on their bridge, then it has a huge L2 asset pool. And the small L1 asset pool, it is going to use our trustless bridge, and that way balance the asset pools between L2 and L1. So now that I've hopefully gotten you excited about Optimism, where can you get for more information? One place is our help center, help.optimism.io. If you go there, you can see information on getting started, how to use Optimism, etc. And if English isn't your best language, we have translations to a bunch of other languages. Alternatively, you might want to go to optimism.io itself, and here you can see not just information about us, but also about all of the applications. You can see incentives, NFTs, bridges, etc. Additionally, if you have any questions, you can go on our Discord. To get an invitation, go to discordgateway.optimism.io. It will just make sure that you're a human and remind you to never share confidential information and things like that. And if you're just getting started, we have a special getting started workflow for you. You can go to appoptimism.io/get started, and here it would ask you how well do you know Optimism, and then, or how well do you know crypto in general, and then it would tell you what you can do and explain exactly how to do it. Of course, one of the first things you need to do is to bridge ETH into Optimism, because without ETH you can't run any transactions. If you want a more playful version of this, we also have op.atlantis.world, which gives you a more playful and retro vibe version of the same thing. So here we are. We can talk to users. Okay, let's get some quests. and we walk around the world. We enter various buildings like City Hall and get the basics of information from various systems, from various creatures that we talk to.